Okay, now we're going to talk about electrical potential and potential difference. So here we've got a circuit, we've got a battery, and it's connected to two light globes, globes A and globes B. So for this particular discussion, we're now going to assume that charge is flowing out of the battery as conventional current. In other words, it's flowing in that direction. This is the positive end of the battery, and this is the negative end of the battery. We're also going to assume that this is a 9-volt battery. And what that means is that each coulomb of charge that exits our battery, remember, a coulomb of charge is a whole lot of equivalent of, if we're talking about electrons, it'd be 6.24 times 10 to the power of 18 electrons. Now we're talking about the equivalent positive charges. But that's a lot of charge there, individual elementary charges, and that coulomb of charge would contain 9 joules of energy. So a 9-volt battery will give each coulomb of charge 9 joules of energy. And in fact, it's electrical potential energy. Oops. Electrical potential energy, PE for short. Okay, so this positive charge now makes its way around our circuit. Now let's look at it when it's about here. So remember, we started here, there's our coulomb of charge, and it's now moved to this position here. Now, assuming that the metal wire that this charge is moving through doesn't heat up and it doesn't offer any resistance to our charge, it will still have 9 joules of energy. So if we measured the energy as it came out of the battery for that coulomb, and let's say it was 9 joules, and we measured it again when it got to this position here and was also 9 joules, then we can see that it hasn't lost any of its electrical potential energy. It's still got 9 joules of energy for each coulomb. So that coulomb still has 9 joules of energy. And so if we were to measure the difference in electrical potential, we would expect that to be 0. Because the difference between those two positions, between this position A and this position here, B, the difference in the energy level of that coulomb of charge is 0. So we say, the way we describe that, it has a potential difference of 0. And we use a voltmeter to measure potential difference. So if we were now to connect a voltmeter, let's say we'll put one of the terminals of the voltmeter here, and we put the other terminal here on the circuit, and we connect both of those to our voltmeter, we would expect the voltmeter to register 0 volts, because there's no difference in the electrical potential energy of the coulombs at each of those two positions. And so no energy is lost. Now let's consider now that coulomb of charge was originally here. There it is. And remember, at that position there, that coulomb has 9 joules of energy. Now let's imagine that it now passes through our globe. So it's traveling through here, it goes through the globe, passes through the element or the filament in there, and then emerges, coming out the other end of the globe and continues down here. Now, assuming the globe is turned on, which it will be, and it's creating light energy and it's creating heat energy, then that light and heat must have come from somewhere. It's actually come from the electrical potential energy that's been carried by that Coulomb of charge. And so we've got this heat and light being created here. And just remember, this is a 9-volt battery. And also, one thing I forgot to say was that both of these globes are the same. So these two globes, globe A and globe B, are identical. So if we now measured the electrical potential energy of the Coulomb of charge just before it goes into the globe, notice that position there, we'll call that position A. And if we measured the electrical potential energy of that same Coulomb of charge as it emerged from the globe on the other side, at position B, we would expect that the charge as it comes out of the battery would have less energy, because it has given some of its energy to the globe. And if each Coulomb of charge, let's say, gives up 4.5 joules of energy, so if each Coulomb of charge is giving 4.5 joules of energy to the globe in terms of heat and light, then as it comes out the other side, it's going to be less 4.5 joules. In other words, it was 9 joules going in, and now it's 4.5 joules coming out. And so it's actually got a difference of 4.5. Now this is the important part. It's a difference of 4.5 joules per Coulomb, or volts. So remember, 1 volt equals 1 joule per Coulomb. So it's basically saying a potential difference of 1 volt means that for each Coulomb that passes through that object, there is a difference of 1 joule of energy. So if we now take that Coulomb of charge, here it's here, and now it moves through the second globe. There's that Coulomb. It's moving through the second globe. Will pass through the second globe and emerge out the other side. And if it too glows and releases heat and light, and it's the same as the other globe, so it's going to, for each Coulomb of charge that passes through, it will convert 4.5 joules of electrical potential energy into heat and light. And so you can probably guess, if we were to put or compare the electrical potential each side of that globe, we would see it also would be 4.5 volts, or joules per Coulomb. So that would mean that if we were now to compare, look at the electrical potential at various positions around our circuit. At this position here, charge as it came out of the battery had 9 joules of energy. And because there's 9 joules for every Coulomb, we say that it's at 9 volts of electrical potential. Here, it'd still be at 9 volts. Here, still at 9 volts, and so on. Still at 9 volts. It hasn't lost any energy yet. Now as it passes through this first globe, and it comes out the other end, it's now dropped down to 4.5 volts, or 4.5 joules per Coulomb of charge, because that amount of energy has been converted to heat and light. Now it's still at 4.5, 4.5, 4.5. Now it's going to lose another 4.5 as it goes through the second globe. Therefore, when it comes out the other side of that second globe, it will have 0 electrical potential energy. And as it returns back to our battery, that is exactly the state it will be in. It'll have 0 volts, or 0 joules of electrical potential energy for each coulomb that re-enters that battery. And when it re-enters the battery, it gets basically re-energized, if you like, and then re-emerges out of the battery again with another 9 joules of energy. And so it's the electrons that are actually, as they move around the circuit, they're actually just conveying energy. They're like a conveyor belt, carrying energy with them to various places around the circuit, where that energy is then transformed to other forms of energy, such as heat and light. And electrical potential is the amount of energy that a coulomb of charge would have in any given position in the circuit, whether it be here or here. And remember, here it would be 9 joules per coulomb. Here would also be 9 joules per coulomb. And that's the electrical potential at any position around the circuit. The potential difference, which is what a voltmeter measures, is the difference in electrical potential. So to recap, if we were to put a voltmeter across this globe, because it lost 4.5 joules of energy per coulomb, we would expect to see a potential difference of 4.5 volts across that globe, and also across this globe. So hopefully that's explained the difference between electrical potential and potential difference.